Hello and welcome to the video that's going to talk a little bit about section 1.3 in our textbooks, measuring segments. What we're going to try to do here today is we're going to start the basis of applying the midpoint formula and the distance formulas to just one dimension. We're going to deal with two dimensions in the next section, but for right now we're just going to deal with one dimension in the number line. So we're going to look and understand how we're going to compare and find lengths of segments. So when you're done with this, you should be able to have a basic understanding of how this is going to work on a number line. And if you don't, you can go back and watch the video a couple more times or pause it where you need to. So the first thing I want to do is make sure we understand what a segment is. We talked about this in the last lesson, but a segment is a part of a line right here that consists of two endpoints. In this case, H and J, and all the points in between them. You can think of it as part of a line. So if I have a line here that I've drawn, it's a really detailed line going on here, and I have points X and Y on this. If I look overall, XY is this line, XY is the entire line. But if I just want to talk about the segment in between the 2 points, what I'm going to denote is XY with the segment symbol over top, no arrowheads on the end. And the way I name it, remember, is by its endpoint. So in this case, this could be segment XY, or this could be segment YX. It doesn't matter which way you go, but you need to have a start and you need to have a stop to your naming. If there's a third point on the line, I saw this in some cases on the previous quiz, if there's a third point on this line, in this case point Z, I'm not changing anything. If I still want to talk about this entire distance right here between X and Y, the way I'm going to denote it is either segment XY or segment YX. This Z in the middle doesn't cause any issue. It's like if I'm driving from here to Madison, I want to find the distance between here and Madison. I don't bring up Sauk at all in my conversation. Yes, it's on the way between here and Madison, but I'm only concerned about finding the distance between here and Madison, not Sauk. So let's just take a little second, give yourself about 15 seconds, and I have this segment down here, A and C, and these 3 points that are on the screen. What I want you to do is I want you to think about what kind of information can you tell me given just that picture below, okay? I'll give you 20 seconds. You have about 5 more seconds left. Okay. See about what you thought compared to the answers that I'm going to come up with here, okay? The first thing that I'm noticing here is that points A, B, and C are collinear. A, B, and C are collinear. Because even though I have only a segment shown here, I have all the points lie on that segment. They all lie on a line, so they're collinear. The next thing that I notice is that point B is between point A and point C. Like in my example that I talked about before, when I was going from here to Madison on my trip, Sauk is between the two towns. It's not exactly in the middle, but it's between the two. It lies on this line between points A and point C. The last thing then that I'm also looking at here is if these are distances, I'm looking at this and saying, hey, that distance from A to B, if I add it to the distance from B to C, it gives me the whole overall distance. Using my driving example from here to Madison, if I take the distance I drive from here to Sauk and add it to the distance I drive from Sauk to Madison, I'm going to get the entire trip from Baraboo to Madison. And this idea right down here is a very important part of what we talk about in geometry. It's one of our first big theorems or postulates that we come up with, called the segment addition postulate. And the segment addition postulate says this: if 3 points A, B, and C are collinear, they have to be in a line. And B is between A and C. So right here in my picture, I have B between A and C. Then the distance from A to B is the same as the distance from B to C. That's our key thing that we're going to try to look at here when we're talking about distances, is being able to add pieces up to get the whole thing. Now, I also mentioned earlier that just because B is between A and C doesn't necessarily mean that it's smack dab in the middle. It's not an equal distance. If I'm looking up here at my picture, on the top picture, this first distance could be 3, the second distance could be 7. So that makes the entire distance 10, 3 plus 7. But down in this bottom picture, we've introduced this new term called the midpoint. And the midpoint is the spot specifically in the middle, so that this distance from A to B is exactly the same distance as B to C. So in my drawing that I have down here, AB would be 5, BC would be 5. It splits it perfectly in half. So what I want to do next is I want to just run through a couple scenarios with some doodles to help you kind of hopefully understand what's going on here. So if I have a segment, in this case I'll draw a segment here like this. And I'll call this point M, I'll call this P, and I'll call this point over here W. Okay? I know all 3 points are collinear. I know W is between M and P, but it's not specifically the midpoint. And then I can say that MW is 10, and I know that MP over here is 14. Well, if I want to figure out what WP is over here, all I'm going to end up doing is maybe I give this thing a variable, I'll call it X, because if something we don't know what it is, and it can be any sort of number, we're just going to give it a variable because it works a lot better than a question mark in a problem. I know that 10 plus X has to be 14. Or as most of you probably figured out already, X has got to be 4. It's a pretty simple, straightforward one. Now if I have another segment here, I'll call this AB, and I have a point that I'm going to call the midpoint here. I'll say this is point M. I'll make a better M there. I'm going to say that this is point M over here. One thing that I can do is to show that segment lengths are the same. What I can do is I can put little tick marks on it. And that little tick mark right there is telling me that AM is congruent to MB. Those two segments are the exact same length. Now, if I have a line, a segment, or a ray that intersects here at point M, anything that comes in at that point. So if let's say I've got this line. I've got this line that comes through here. Okay, and I'm going to put a C over here. So I have line CM. What I've said now is CM is a segment bisector of segment AB. A couple things to notice. First of all, it's a segment bisector because AB is a segment. The other part to make note of is this phrase bisect right in there, which means cuts in half. This line CM comes and cuts right through AB right here at point M. That's the midpoint. So anything that comes in at this midpoint is considered a bisector. Here's another case. Here's a ray coming out. This is L. So now I have ray ML is a segment bisector of AB, of segment AB. Okay, let's look at a couple other images here quickly. Now notation-wise, up here I have two segments. I have segment AC and I have segment AB. Notice the tick marks. I'm telling that they're the same length. However, are points A, B, and C in this case collinear? I don't think so, because I've got this like angle thing going on here. They're not collinear. So I can't say anything about point A being between B and C. I can't say anything about the segment addition postulate where they add up to certain lengths. They're not in the same line, so none of that holds. The only thing that I want to stress here in this case is I want to stress the notation. If I say segment AB, notice this notation here, segment AB is the same length as segment AC, what I'm going to use is this congruent symbol. It's a little equal sign with a tilde over top of it. And when I have that congruent symbol, it means that the segments are congruent or that they're of equal length. But notice, in either case, these over here are names. This segment AC and segment AB, those are names of the segments. The difference over in the notation part is when I'm working with names, names can be the same. So if I have a person named Susie in my class and another person named Susie in my class, I can say they have the same name. But when I take the hat off, I take the segment symbol off the top up here, and I just have the letters, now what these represent is these represent numbers. This might represent Susie's age. And now numbers can end up being equal. Numbers can end up being equal, so not congruent. So when I'm looking at this, I'm saying this number length is equal to this number length. Be careful on how things are worded. If you're telling me segments, you got to give me congruent. Notice, everything has hats. These have flat hats, this has a tilde hat. No hat, no hat, no hat. Maybe you can use that to remind yourself. Okay? So let's take a look at some examples here. So on your note sheet that you should have that you're working with, I have some examples on the back side. So on the front side of your sheet, you should have been writing down the material that we've been talking about. On the back side, we got this example right here. The first thing I'm looking at is what is the length of BC? Notice no hat. So what the question's asking me is how long is this length from B to C? So if I notice where C is, it's at -3. And B is at -6. Well, if you have a number line, you should be able to count the difference between the two of them. The biggest thing you need to remember is lengths can never be negative. Lengths are always positive. I don't say it's -10 miles from here to Wisconsin Dells, and then it's 10 miles the other direction. It's always 10 miles. Your car only registers positive distance. We're only measuring positive distance. So when we look at something like this, if we're going to do this thing arithmetically, what I'm going to do, distance between things is a subtraction situation. And since I always want it to be positive, it's going to be absolute value. So in this case, what I'm going to do is I'm going to take -3 plus, or -3 minus a -6. Well, what you understand from subtracting negatives is I add the opposite. And I'm going to end up with -3 plus 6, which is the absolute value of 3, or 3. I'm just showing this to you algebraically right now, but there's nothing stopping you from going through and counting. Those are 3 away. So what's BD in this case? Well, BD starts at -6 and goes to +1. So I'm going 1, 2, 3, 4, 5, 6, 7. So BD, the way I'm going to denote this, I'm going to say BD equals 7. Please practice working on good notation. Now look at how we're asking question 3. Is segment AB congruent to segment BC? Do they have the same lengths? Well, how far is AB over here? AB is 1, 2, 3 units away. And how about BC? That also is 1, 2, 3 units away. So because they're both 3, AB is 3, BC is 3. Therefore, I can say segment AB is congruent to segment BC. And the last one, is BC congruent to CD? Well, BC, 1, 2, 3 apart. CD, 1, 2, 3, 4 apart. Well, BC is 3, CD is 4. I know those two lengths aren't the same. So what I say is BC is, I do the congruent symbol, I say it's not. I put a slash through it. Not congruent to CD. Okay? Let's try the other two. Where should we put point E so that E is the midpoint of CD? Well, when we're talking about midpoints, what helps us figure this out a little bit is averages. If you think about how you average two things, if you got an 80 on a first quiz and you ended up with a 100 on the second quiz, your average would be 90, right in the middle. Or 80 plus 100 is 180, divided by 2 is 90. We add them and divide by 2. So if I look and see where C is on here, C is at -3. And D is at +1. So if I take -3 plus +1 and I divide it by 2, that's going to get me my midpoint. So -3 plus 1 takes me to -2. Divided by 2, it's going to be -1. So if I put point E right here at -1, that works out nicely because my distance between the 2 points then, this distance here is 2, this distance here is 2. Everything works out nicely. Now the second question is a little trickier. The second question is asking, where should point F be located so that D is the midpoint of CF? Things just got a little bit crazier here. Where should F be placed so that D is the midpoint? So I want point D here to be the midpoint of some point CF. I don't know where F goes. Do you have an idea of what we're going to do? Well, if I want D to be the midpoint of CF, what that's telling me then is this CD has to be equal to DF. Those two lengths have to be the same. And if I look at my picture up here, CD is 4 units away. So I know that CD is 4. So DF has to be 4 more units away this way. I have to go 4 more units. So what I'm going to do for my work is I know point D is at 1. I'm going to add 4 more to it. It should be at 5. So point F should be placed up at 5. Last example here before I let you work. Points G, H, and I are collinear, and H is between G and I. If GH is 12, GI is 23, what is HI? There's a lot of information there. Some of you might catch this right away and figure out what to do and be able to work without a picture. If not, there's no shame in drawing a picture, and it doesn't have to be crazy detailed, just useful for you. So let's go through this a little bit at a time. G, H, and I are collinear. So I'm going to make G, H, and I collinear. And it also tells me that H is between G and I. So when you do something like this, don't put it right in the middle unless it says it's the midpoint. So I'm going to put it a little bit off of center. And there's point I. G, H, and I are collinear, and H is somewhere between G and I. If GH is 12, okay, that gives me something to work with. GH is 12. And GI is 23. So this whole distance here, this whole thing here is 23. It wants to know how big HI is. Now, at this point, you probably know what to do subtracting it. You're going to be fine. I'm just going to show you algebraically because for the stuff we're going to do next, we want to make sure we have an algebraic understanding. So I'm going to say 12 plus x, piece and piece, has to equal the whole using my segment addition postulate. I'm adding segments together. Well, I subtract 12 from both sides, and I get x equals 11. What I'm going to say is hi has to equal 11. Notice no hat on the top because I'm talking about a length. So I'd like you to pause the video for just a little bit, and I'll give you and work about 10 minutes or so on the first part of the homework on page 24, 9 through 17 odds. Okay? When you're done, unpause the video, and we'll pick up and we'll do a couple of bit more of the trickier examples later. Okay? Okay, I hope those problems didn't go too difficult for you. They tried to pretty much stay with just numbers, nothing too algebraic. Now this latter half is going to work a little bit algebraically using the segment addition postulate. So we're on example 3 on our note sheet here. This question asks us to find the value of y and then use that to find PQ. Here's a perfect example of the segment addition postulate. I know this little piece from QP and this little piece from PR goes together to make the whole piece from QR. So what I'm going to do is I'm going to write out what my segment addition postulate looks like just quickly. QP plus PR is equal to QR. And now I'm going to substitute in my lengths. QP is 2y. PR, 21. The whole thing, 3y plus 1. Now it's just plain old algebra that you did last year. Gather your variables on one side, gather your numbers on the other side. We want to get y by itself. So the first thing I'm going to do is I'm going to get this 2y over to the other side with that 3y. I need them together. It doesn't do any good with them all spread out all over the place. So what I'm going to do is to get this positive 2y off of this side here, what I'm going to do is I'm going to take it away from this side. And then to make sure the equation is balanced, I got to take it away from the other side. So I'm left with 21 equals y plus 1. That's awesome. I got a 1y now. But this 1 is in the way. I got to get that over to the other side. So the way I'm going to do that is I'm going to take it away from the right side. I don't want it over there, so I'm going to take it away. But to keep things balanced, take away 1 from the other side. Subtract y is 20. Awesome. We found the value of y. That's our first pit stop. Now, how am I going to use that to find PQ? PQ, I know, is 2y. So I'm just going to substitute it in. 2 times 20. So PQ ends up being 40. Basic, simple segment addition postulate problem. That's example 4. Or example 3. Example, if xy is 7, okay, and that's labeled on our picture, and xz is 30. Xz, what is xz here? Xz looks to be the entire distance. I know this entire thing is 30. Any chance that you have to work with pictures, label them, use them. We're going to be using a lot of visuals this year in geometry. What is the value of t? Well, I've got segment addition postulate going on here again. xy plus yz is equal to xz. So xy is 7, yz is 2t minus 1, and I know the whole thing, xz is 30. Let's combine some like terms. So I get 2t, 7 minus 1 is 6, I get 30. I have to get t by itself. So the first thing I got to do is get that 6 off of this side. So I'm going to take 2t plus 6 equals 30. I'm going to subtract 6. 2t equals 24. I want the t by itself. This 2 needs to go here. So to undo multiplying, we divide by 2. I get t equals 12. The question was asking me what's the value of t? T is 12. That's what I'm going to show my answer as, but I'm going to show the work that I took to get there. So I understand the steps, and you can show me that you understand what's going on. You're not just guessing and checking. The last example, 5. M is the midpoint of Ln. Well, this is nice. It's the midpoint. If M is the midpoint, what does that tell us about these two lengths? It should be telling you that this segment here is the same as this segment here. So I know, because it's the midpoint, I know that LM has to equal MN. Notice I have lengths, so they're equal. Length of LM is equal to the length of MN. So what I'm going to do is I'm going to say 3x equals 2x plus 2. Let's gather our terms. I want this 2x to join the 3x over there, so I'm going to subtract 2x from both sides. So I'm just left with a 2 over on that side. I'm left with an x. Well, that was nice. X is 2. Well, it didn't ask me what x is. It asked what LM is. So to figure out what LM is, I know that LM is 3 times x. I know x is 2. So 3 times 2, or LM, is 6. And when it asks me what is LN, well, I know they're the same thing, so LN has to be 6. The biggest thing that you need to make sure you understand is you're going to be piecing things together. Parts equal wholes in the segment addition postulate. And if there's a midpoint involved or a bisector involved, you know that one piece equals the other piece. Those are the two main things. So if you have any questions on any of the stuff that we talked about, either go back, replay the video, pause it, figure out what you need to, talk to a classmate, or stop and see me before school, after school, or once we start doing enrichments. Stop in and see me. Let me know if you've got any questions. I'll be glad to help you out. But don't be afraid to draw pictures. So here, with the time that's left, is finish up the homework. The homework's going to be page 24 and 25 in your book, 9 through 29 odds. So you can double check to see if you're doing right, but make sure you show me some work. And 36 to 40 all. If you get done with this, I would strongly suggest going through IXL and keep practicing. We're doing good progress as a class. And start working your way through section B on there. Okay? Thanks much.